Yeah, I know. Okay, so yeah, let's get started. Yeah, I think this is working. Okay, so unfortunately, so basically today I finished like the final exam thing for like the material that we were using. So remember like this thing. So I don't have that anymore, unfortunately. So we're gonna use I guess Khan Academy. So basically, what we learned so far is uh, we learned yeah, we learned lots of stuff, not just that. So we learned some. Let's see, what was it? Let me get my thing. Okay, so we learned about like conics. Remember those? It's where you had like the parabolas and stuff, like this thing, and like remember like the cone thing image, where it was intersecting the cone. So it was like that, and then the thing was like this, and that was the parabola. Let me just share a whiteboard. Okay. Oh, okay. There we go. Okay, so basically, we learned some conics. And so this was basically like the stuff like, let's just review this stuff. So do you guys remember the conic equation?
Wasn't it like, yeah, it was opposite over,
No, you're talking about trigonometry. Yeah.
yeah, I'm talking about
Yeah.
y equals a minus 8 in parentheses plus k. I think it was a minus 8 squared plus k.
Okay. So that was for parabola, but this was a long time ago, not yesterday.
I don't think I was there.
You were, I'm pretty sure. I don't remember though. So that was the parabola equation, which is y is equal to a x minus h squared plus k. So the conic equation is like a super long equation where it's like a x squared plus b x y plus c y squared, and you have plus d x plus e y plus f. I don't think you guys remember this, but like, yeah, this is the conic equation. And remember the discriminant where it was like b squared minus 4ac? And that was how you could tell between the parabolas and the hyperbolas and stuff. So can anybody tell me the circle equation?
Okay, so I think the circle equation was a minus 8 squared plus y minus k squared.
Okay, so you keep saying a, but I think you mean x. You got most of it right, so it was x minus h squared plus y minus k squared is equal to, do you know what that's equal to?
R squared.
Yeah, it was r squared. Good job. So, can Rohan tell me the hyperbola equation? Okay, so it's x minus h squared divided by a squared minus y minus
y minus k squared over b squared, I think.
Yeah, good job. Is equal to, do you know what it's equal to?
R squared?
No, it's just 1. Remember, hyperbolas don't have a radius, so hyperbolas look like, yeah, they look something like one parabola and then a second parabola, even though they're not really parabolas. Remember this? Like it looks something like this, and this, like that, or something like that.
Yeah.
I can't really draw well with this thing, but you know, yeah, something like that. Okay, so the ellipse equation is very similar to this one, but basically this is the ellipse equation. Ellipse. It looks like a J. Whatever. Ellipse. And so this is basically x minus h squared divided by a squared plus y minus h squared divided by b squared is equal to 1. So the only difference here is this plus. If it was a minus, then it would be a hyperbola. So do all of you see that?
Yeah.
So yeah, now let's go on to the next part. So basically, I class I can go up that. Okay. Sorry about that. I accidentally muted myself. So basically, here you're basically okay. So then we learned about. Does anybody remember the? Okay, oops, that's a bad R. Does anybody remember the ratio? I don't think many people were here for this. Yeah, maybe. Rational zero theorem. I think Siddharth was here for this though. But I don't really remember. So Siddharth. Okay, so basically what this theorem stated was that if you had a p, so p, and let's say that you have an equation of y is equal to x squared plus something x plus just x and plus 1. So let's say you had a p-value of the factors of this. So do you all of you see this? This is called the constant because it doesn't have a variable attached to it. So these are the factors. Factors of the constant. It's really hard to write. Okay, so constant. So constant. And Q is the factors of the leading coefficient. So you see right here, this invisible space, there's a 1 over here, also over here. But this is the leading coefficient, because there's x squared, so that's the biggest exponent. That's the biggest, like, this has the biggest degree, this term has the biggest degree. So the leading coefficient is the coefficient of this term. So basically we'll just take the factors. Okay, that's bad. factors of the leading coefficient. Leading coefficient. Okay, that does not look like leading, whatever. Okay, so leading coefficient did not there. Okay, leading coefficient. That looks like a B. Okay, there we go. So factors of the leading coefficient, and so if you do P divided by Q, then you get a possible root slash 0 for the equation. For the function or the equation, which is this right now. Oops. Okay. Come on. This. So for the equation, and yeah. So let's do P divided by Q, and we get 1 divided by 1. So let's choose a harder thing. So we know that 1 divided by 1 is possible, x-intercept or root or 0. And yeah, that's obviously true because like if you graph this, you get something like a parabola that looks something like this with a thing at the origin or something. You know what I mean? Oh no, you're not gonna get this. You're gonna get, I think, something like this. Or something like that. I don't really remember. Or it might be translated like this. Yeah, I think it's something like this, where there's a point right here where it's 1. And yeah, this would be that. But let's look at something harder. So you get the eraser, erase this. Okay, so basically we have, let's write another equation. Y is equal to 6x cubed plus 3x minus 9. Okay, so does anybody want to tell me all the possible factors? Sorry, all the possible roots of this function?
Well, the constant is -9, so factors are plus or minus 1, plus or minus 3, and plus or minus 9.
Yeah.
Then Q will be the factors of the leading coefficient, which is 6. So it'll be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Then we just divide. So it will be P over Q, which is 1. So it can be 1 over 1. Then it can be 1 over 2. Then 1 over 3. Then 1 over 6. Then 3. So you just divide all of them. So you do plus or minus 1 over plus or minus 1. And then, yeah, plus or minus 1 over 1. And then 1 over 2. And then 1 over 3.
Plus or minus 1 over 1 would just be 1.
Yeah, so it'll just be 1. And then you do the next one. And then you do, so plus or minus 1 over plus or minus 1 equals 1. So then plus or minus 1 over plus or minus 2 is 1 half. And then plus or minus 1 over plus or minus 3 is 1/3, plus or minus 1/3. And then you do the same thing for 1/6. So then now we do 3. So plus or minus 3 over plus or minus 1 is plus or minus 3.
Yeah.
And then plus or minus 3 over plus or minus 2 is 3 halves, plus or minus 3 halves.
So we don't really have to write that again.
And then plus minus 3 over plus minus 6 is 1 half, which is what we wrote, so we don't write that.
Yeah.
Then we do plus minus 4. So plus minus 4 over plus minus 1 and plus minus 4. And then plus minus 4 over plus minus 2 is plus minus 2. And then plus minus 4 over plus minus 3 is plus minus 3. And then plus minus 4 over plus minus 6 is 2 over 3. And then we write that.
Yeah. Good job, Rohan. So, so now let me ask you a question. Does this mean that that this function has all of these roots? So does it have like does this function intersect the x-axis at all of these points?
Now, if we narrowed it down, it narrows it
Yeah, good job. Okay, so now basically after you have this, what you could do is you could like try out each of these one by one and see which one is the actual factors. But we're not going to do that because we're not really talking about that. So let me just clear the screen. And let's go on to the next topic. So that was two topics that we covered. And yeah, that was the rational zero theorem, whatever you want to call it. And so, do you guys remember direct variations, indirect variations, and joint variations? Direct variations, indirect. Variations. Okay, and then we'll have and then you have joint. Joint variations. So basically all of these, basically they're like this. So I'm just making another thing. Another thing. Okay, so now so this column is where all the it's where like the relationship goes. So the relationship between like the x and y for direct variation is super easy. Basically it's just x. Okay, excuse me. It's just x1 over y1 is equal to x2 over over y2. Okay, so now let's go on to the equation part. So the equation of a direct variation is super simple. Also, it's just y is equal to k times x. So now indirect variations. So indirect variations, basically they're just x1 over y2 instead of y1 now is equal to x2 over y1. And yeah, that's basically how you do it. And then this equation looks something like x times y is equal to k, or y is equal to k, okay, y is equal to k over x. Yeah, that's basically what it is. Okay, and then joint variation is super complicated. I don't even know what you use this for or how it works. Okay, so basically joint variation is basically anything except these two. So if it doesn't match these two, then it's a joint variation. So joint variations, basically they just look super complicated and everything. So it's y1 divided by y2 is equal to x1 divided by x2. but then you also have z's. So you have z 1 divided by z 2. And yeah, that's just pretty complicated. And so this equation looks something like
Okay,
y.
so wait. So y over 1 over y over 2 equals x1 z1 over x2 and z2?
Yeah.
Okay.
And remember, if there's no operation between these two, between two variables, or two numbers and variables, then there's a multiplication sign over here. So yeah, that's basically what joint variation is. And yeah. Okay, so let's look at an example. So did all of you write this down? Because I'm going to erase it. Okay. Seems like a yes. So, yeah. So let's look at a problem. So basically you have, let's say that you have a table of values like that, and then you have one. Okay, no, I don't know what I'm doing. Okay, so let's say that this is x and this is y. So let's say you have an x value of 0 and you have a y value of 0. Super simple right now, right? And then you have an x value of 1 and you have a y value of 2, and you have an x value of 2, y value of 4, x value of 3, and y value of 6, and then there's the last one, x value of 4, and a y value of 8. So what kind of function do you think this is, guys?
Linear.
Okay, but which one of the variations? Is it a direct variation? Is it an inverse variation? Or is it a joint variation?
I'm not exactly.
I think it would be an indirect variation.
Okay, it's actually a direct variation.
Please go over this again.
Okay, yeah, sure. So basically, how you would find this is because you remember the formulas, right? Did you write it down? It was
Yeah, it was y equals k and
yeah, but not that, like the other formula, like with the x1 and the y1.
It was x1 over y1 equals x2 over y2.
Yeah. Good job. So basically, yeah. So this is a direct variation because let's just choose an x1 and a y1. Let's say that this is our x1 y1 pair, and let's say that this is our x2 y2 pair. Do you understand that until now? Since this is x and this is y, this is x1, this is y1, this is x2, this is y2. Okay? So now let's substitute the values into here. So you have x1 as 1 over, and then y2 as 2 is equal to 2 over 4, because x2 is 2 and y2 is 4. So yeah, you understand up until this point, right?
Yeah.
So this means if you simplify this, this is right. So yeah, this is right.
Also, it's proportional.
Yeah, this is proportional, yes. See, this looks something like this. It goes through the origin, because 0, 0 is a pair. Doesn't look like it goes through the origin, but whatever. Yeah, it goes through the origin and everything. There we go. So it goes through the origin, and yeah. Yeah, you shouldn't choose 0, 0 when you're doing that thing. Yeah. That's why I chose this pair instead of this, instead of 0, 0. So yeah. Let's try this with the inverse. So this equation is obviously I'm trying to find it. X1 divided by y2 is equal to x2 divided by y1. So let's try it in here. So we have x1 has a value of 1 and an x2, an x2. So let's just do the x2 first. It has a value of 2, just like before. Now y2 has a value of 4, and y1 has a value of 2. So this obviously does not work because 1 is not equal to 1 over 4. So this is obviously not true. That's why it's not an inverse variation. So do you guys kind of understand that and why that works and stuff?
Yeah, but what about the joint variations? Like, we gave it 3 values. It had an x and a y and a z. What was the z represent?
I actually don't know. I haven't. So the thing I was studying didn't say much about that, so I really don't know how. I have to search it up also. So what is joint variation used for? Oops. I don't think you can see the screen. Sorry about that. Okay. Joint variation used for. Let's wait for this to load. So let's see varsity teachers. Joint variation graph. Come on. Okay. So it says this is what it looks like. So there's like an x to the power of 3 function or something like that. And then there's and that keeps on repeating for and ever and ever. Yeah, that's what it looks like, I guess. Or it can look like this. I guess it can look like a bunch of stuff then. This, anything basically. That's pretty cool. I didn't know that. Okay, so yeah, I really don't understand much from this, except that it's anything other than an inverse and a direct. But like that's not explaining much since we already knew that. So yeah. Let's get back to the whiteboard stuff. Okay, so yeah. Okay. So let's go on to the next topic. So does everybody kind of understand inverse variations and direct variations? Hello? Okay, yeah, good. So the next thing we're going to go over is logs. I'm pretty sure most of you know that because they're pretty cool. So logs. So these are basically like inverse exponentials. So like they're like the exact opposite of exponentials. So you know how like exponentials, like you can raise something to a value. So like you have 2 to the power of 3 is equal to 8, right? All of you know this, right?
Yeah. So log
Yeah.
log base 3 of log base 2 of 8 is 3.
Yeah. Log base 2 of 8 is 3. Yeah, good job. So, so logs have some weird properties, which are also pretty cool, and they can be exploited for uses, I guess, if you want to solve some equations or something. So, basically, the first, and these correspond to exponential properties as well. So, Dot, do you remember some exponential properties from like the class before this one? Remember, like we had, let's say, the power of a power rule. So like p, and then that was equal to like, uh, so let's say, and then there was p. So let's say that all p is equal to 2. So it's 2 to the power of 2 to the power of 2. So this is equal to,
Yeah. Yeah. So if you want to, so that is equal to 2 over 4, because it's like power of 2. Like, there's 2, the power of 2 squared, and the 2 on top, you're going to have to multiply both of the 2, since there's one 2 in the parentheses and the other one isn't. You're going to have to multiply both of them. And after you multiply both of them, you get 4, and then you just do 2 to the power 4, and you get your answer.
okay. So that was a little bit confusing, but basically what he said was, if you have, let's say you have b to the power of a to the power of c. So basically this is equal to b to the power of a times c.
That's what I said, yeah.
Yeah. So yeah. So let's see the corresponding property for this. So basically, let's see, you have log. Okay, oops. Well, I think we're gonna have to start the meeting again. So yeah, let's do that. Okay, guys. So let's get started again. Let me share my whiteboard again. And so, where were we? We were talking about exponentials, and we were talking about power of power rule. So my drawing tool. There we go. And so basically we have b to the power of a to the power of c is equal to b to the power of a times c. So let's look at the corresponding log property of this. So we have log base b of a to the power of c. So this is basically the same thing as c times log base b of a. So this is useful the other way around. So if you have,
That's so weird.
yeah, it is pretty weird, but like, yeah, this is the same thing as this. See, if we like write some numbers in here instead of like variables, so it'll make more sense, I'm pretty sure. So we have 2 to the power of 2 to the power of 3. And so over here, which is, we have the same thing, which is log base b, which is 2, and you have the answer, which is 4 to to the power of 3. So yeah, let's see this. So over here, this would equal 2 to the power of 2 times 3, which is 6, right? So let's calculate the value of this. So we have 2 times 2 times 2, which is 8. And then we have another 2 times 2 times 2. And so that's 8 times 8, which is 16. Actually, no, that doesn't work. Yeah, that doesn't work. I think we're going to have to use 60. Oh, yeah, I just did it wrong. It does work. It's 8 times 8 instead of 8 times 2. It's 8 times 8, which is 64. And yeah, that's basically how you do it. And so let's try to do something for this. So you have log base 2 of 4 to the power of 3. So 4 to the power of 3 is obviously 64. So that's log base 2, yeah, of 64. Which is, it's actually not 8. It's 6. Because 2 to the power of 6 is 64, not 2 to the power of 8. Okay, yeah, makes sense. So now let's just rewrite this, but instead let's use this property and see what that gives us. So we have log base 2 and 4 to the power of 3 is equal to 3 times log base 2 of 4. And so this is equal to 2 times 3, because 2 to the power of 2, 2 to the power of 2 is 4. So this equals out to 2, and then we have times 3, and basically that's 6, because 3 times 2 is 6. And yeah, we got the same answer. So we know that it definitely works. Even though it's a little bit complicated, it still works. And most of the time, it'll be more useful like this. So you have c times log of b a, and so now you can just like translate this into here, like that. So you have log base b of a to the power of c. So it's more simplified if you have numbers over here. So yeah, that's basically how you use it. It's pretty cool, and it's used for solving like logarithmic equations, because like you don't have the same like privilege with like real numbers as when you have variables. So let's try to solve a log thing with that. So let's say you have log base 10. So basically just log of 100 to the power of x is equal to log of 1.
Wait, you didn't give the log a base.
What?
Okay, you just put log on and the 100 to the power of x. You didn't put the base.
Yeah, so if you don't have a base, then it means it's automatically 10. See, if you look on your calculator or something, there's like a log with no number under it. So that means it's just a log base 10. This is read log base 10 of 100 to the power of x. And so let's try to find the value of this. So we yeah. But let's just use the property to find it out, because normally like the numbers won't be this simple. So yeah. Yeah.
So now we can solve log of 100. So log base 10 of 100 is this graph we printed is what 100. So from square root of 100, so we get 2x. So x is 2. Let's say this is log base 10 of 100. So you see see that there are 4 zeros after the word, so that means it's just 4. So if you're choosing 4, then x is equal to 2.
Yeah. So x is equal to 2. Yeah, that's how you would solve it, basically. Yeah, but what I would do is, instead of like solving the logs first, I would like isolate the x first instead. So what I would do is I would just have x is equal to log base 10,000. Yes, I know it's the same thing, but it's like pretty important. You have to do this first. It's like, yeah, it's super important. So you have log base 10,000 divided by log base 100. Yeah, and then it's basically the same thing. And you have x is equal to 2 again. Yeah. Yeah, good job, Rohan. You got the correct answer, yeah. So, yeah, let's go on to the next thing. There's a few other properties, but I'm not going to go into it super deep. So, let's just look at one more property of logarithms. And that's basically the last one, basically. I mean, not really, okay? So let's just look at 2 other logs properties, because the last one is going to be super important. So, we have the product rule. So let's look at the equivalent. Let's look at the equivalent of this, but for exponents here, exponents. So you have 2 to the power of 3 times 2 to the power of 3, and so this is just basically equal to 2 to the power of 6, because when it's like this, you do 2 to the power of 3 plus 3, and you get 2 to the power of 6. So everybody knows that, right?
Yeah.
Okay. So let's look at the same thing, but for logs. So we have 2 to the power of, log base 2 of, what is it, 8 times log base 2 of that, 8, or basically just 8 times 8. And this is basically equal to,
Log base 2 of 16.
yeah, log base 2 of 16. No. No, I think we got the wrong thing here.
Base 2 of 64.
Yeah, log base 2 of 64, yeah. Log base 2 of 64. Yeah, that's what we got. And so let's try to use the actual like thing here. So the actual thing, the actual like rule here is if you have this, then this is the same thing. Let me just write it, 1 second. So you have log base 2 of 8 times 8 is equal to log base 2 of 8, and then you have plus log base 2 of 8. So this is the same thing as this. So does everybody kind of see how that connects to this? Because here you're adding exponents, and so like these are basically exponents, but like they're like backwards, since like the answer you're getting is exponents and not like the thing. So you're adding exponents here, and you're adding exponents here. So yeah, that's pretty cool, right? And yeah, now let's look at the last most useful property if you use calculators a lot. So if you use calculators a lot, then you should definitely remember and use this property a lot. So basically, I'm not even going to give an example for this. Everybody should just memorize this. It's called the change of base formula. And so let's say you have a log, just a normal log. Let's say you have a normal log of log base b of a, and let's say that this is equal to, let's not say anything about that. So this right here So if you look on your like scientific calculator or something, then you'll see that you don't have a log base. You probably won't have a log base of something button over here. Something button. You won't have a log base button. You'll only have a log button, which means log base 10. But we don't want log base 10. We want log base b. That can be like 2 or 5 or anything. Well, let's just choose 5 for now. So let's say that this is log base 5 of 25. Normally the numbers won't be this simple, but yeah, it's pretty much the same. So yeah. So let's actually look at this property. So if you don't have like the log base button, and you only have like a log base 10 button, then what you want to do is you want to transform this into a log base 10. So basically what you have to do is you can have any number as base here. So let's just say x, and you have base b. Sorry, no, we have log base x of a divided by log base x of the actual base. So yeah, this is like super useful if you don't have like a graphing calculator, which has like super useful functionalities and cool stuff. So if you don't have that, then use this. It's really helpful. So basically what you can do is you can transform this into a log base 10 of 25 divided by a log base 10. But remember, both of these have to always be the same. So you have log base 10 of 25 divided by log base 10 of 5. And if you do this, then you get the exact same answer. So everybody knows that log base 5 of 25 is 2, right? So let me use my calculator. Actually, let's do it in front of you. 1 second. I don't think you can see the calculator anyway. So let me just use the calculator. And let's clear the screen. Let's do log base 10 because it's like there's no base. Log of 25 divided by log of 10. Sorry, not 10, 5, sorry. So you have log base 10, sorry, log base 25. No, why do I keep saying base? It's log of 25 divided by log of 5. And basically you get 2. So that means we did it correct. And yeah, it works. Super cool, right?
Yeah.
Yeah. So now let's go on to arithmetic arithmetic series and geometric series. So I think Rohan, you were here for this, I'm pretty sure. So do you remember like the nth term formula? Like the nth term.
I think I remember the nth term. I think it was like a1. A n equals a1. Oh, I remember now. It was a1 equals an equals a1 plus n minus 1 over n minus 1 times d.
Yeah, n minus 1 times d. Good job. Yeah, this is how you find the nth term of an arithmetic, I don't know, arithmetic equation. Sorry, an arithmetic series. This is like an n. Let me fix that real quick. There we go. No, it doesn't. Okay, so geometric series. So you have. Does somebody want to tell me the formula for a geometric series? It's actually not d here, but it's r. because you have a ratio instead of difference. Remember? And then it's divided by 1 minus r. So yeah, good job, Rohan. Actually, no, it's not divided by n minus 1. Sorry, it's not divided by 1 minus r. Yeah, sorry about that. It's just a1 times r to the power of n minus 1. Yeah, good job, Rohan. And so, does somebody want to tell me the sum formula for arithmetic? Yeah, keep going. A of, no, it's actually S of n, because it's the sum. S of n is equal to, okay, yeah, you're right. A of 1, A1 plus AN divided by 2. Just erase this here. Let's make this a parentheses. Okay, oops. There we go. Yeah, that's how you do it. Good job, Rohan. So does and there's actually two formulas for this. Remember, there's S of n.
Yeah, the other one was, I think, the square one.
Yeah.
Plus n minus 1. And then times d. And then close the bigger bracket over 2.
Yeah, good job. For a geometric sequence. I didn't get what you said. Can you say it again? A of n raised to the n. Okay, so you got it kinda right. So first of all, this is supposed to be minus right here, and second of all, it's a of n, and since you have an a of n, you don't have to raise it to the power of anything. You just have to do it times r divided by 1 minus r. Remember, that's super. Yeah, the whole thing over 1 minus r. No, sorry. Only this term minus r. Yeah, only this term minus r. Sorry, only this term times r. And yeah, a of n times r. Only a of n times r. And there's actually another formula for this one also. And that one actually had an exponent, like you said. So you have a of 1 minus a of 1. And remember, this is a 1 and a 1. Yes, I didn't make a mistake. And so this one, you have times r to the power of n minus 1, I'm pretty sure. No, yeah, it's just n divided by 1 minus r. And yeah, this is how you do it. Those are the two formulas. And yeah, that's geometric. So you guys can have a break of a few minutes, I guess. What time is it? Yeah, maybe until 8:07.
Shouldn't break be over by now? Hello? But I said
Yeah,
8 on
sorry.
7.
Yeah. Break is over now. Yeah, I did say 8:07. Yeah. I was just doing something else. Okay. Yeah, let me just clear the screen and we're gonna move on to the other stuff. So, the last thing in this section, real quick. So does anybody remember the sum of an infinite geometric series?
Isn't it over 1 minus r, I'm pretty sure?
Yeah.
So is it a of 1?
Yeah. You got it right. Yeah. This is it. That's it. Super simple. But do you know the restriction of an infinite geometric series?
R needs to be between -1 and 1.
Yeah. R has to be less than 1. It has to be greater than -1. So yeah, good job. So let's just clear the screen real quick and let's move on to the next thing. So now we're going into probability and statistics and stuff like that. So do you remember the formula for permutations and PR?
Yeah. Wait, wasn't it permutation when the order didn't matter?
Yeah, and it was where the order did matter.
Oh, okay. So then that would be n factorial over n minus r squared factorial.
It was not squared. Yeah, but you got everything right.
Oh,
Yeah,
not squared, factorial, yeah.
yeah, that's just it. Yeah, it's just n minus r factorial. Yeah, good job. What about combinations? That's where the order didn't matter.
Is it with n factorial,
Okay.
r factorial, and minus r factorial?
Yeah, good job. So it's r factorial times n minus r factorial. Yes. Yeah, it's super easy, barely an inconvenience. And yeah, that's basically it. There's not many formulas in there. But there is one thing. Remember, do you guys remember how to find the standard deviation?
Yeah, first find the mean, and then you subtract all the numbers in the set from the mean,
Yeah,
and then you square the resulting numbers.
yeah. Subtract and square. And then what do you have to do? Then you're gonna get like 60 answers.
After you square it, I think you add it all together, or you subtract it.
No, you add it. Yeah, you were correct the first time. Add all of them, and then what do you do next?
I don't know.
Then you take the square root because over here you squared it, and then you just take the square root of that answer. And there's the final answer. And that's how you take the standard deviation. Yeah, good job, Siddharth. So yeah. So this is something we haven't discussed, I don't think, but there's another thing called IQR, which stands for interquartile range. If you don't know this already, then you might want to write notes on this because it's
Oh, I
pretty.
know this.
Okay, good. So basically, interquartile range is basically where you have to you have to find the median, and then you have to find Q1, which means the median of this side, this first half. It's called
Known as
Q1.
quartile 1, right?
Yeah, Q means quartile. Yeah, and then you have to find Q3, which is basically the median of this half right here. Q2, and then now you have to find like the difference between. Sorry, this is not Q2. This is Q3. This is median. Okay. Yes, I am running out of time. Okay, so now you have to do Q3 minus Q1 to get the IQR. And yeah, it's much easier than getting the standard deviation. Yeah, it's pretty easy. It's not that hard. So what is this used for? Well, first of all, it's used for finding whether something is an outlier or not. So an outlier is when like something is like way too far from like the thing. Let's say we have a box and whisker plot. So this is called a box and whisker plot, where you're comparing two or like more things, I guess, and you have like boxes on them, I guess, and have it like this, and then you have like something like way off over here, which is like not even part of this because it's like so far away, because the numbers were either way too big or like way too small. So let's say you have 1, 2, 3, 4, 5, and then let's say that all of a sudden you had like 1,000. So this is obviously an outlier, way too far out. So yeah, that's what an outlier is, and you can use the IQR to find outliers. So basically, what you have to do is I forget what it is, but you have to do Q1, okay, Q1 minus 1.5 times IQR, and then that's the lowest part where anything below that would be an outlier, and then the highest part, on like the highest maximum thing where it wouldn't be an outlier, would be Q3 plus 1.5 times IQR. And yeah, that's how you find outliers. So
So the lowest number is Q1 minus 1.5 times IQR, and the highest Q3 plus 1.5 minus IQR.
no, this is times. I
Oh.
didn't mean to write it as a minus, but yeah, it's a multiplication. Thanks for bringing that up. Okay, yeah. That's basically how you do it. That's basically how you find outliers and stuff. Okay. So, does anybody remember the bell curve? What is it? Does anybody remember what this is? Looks something like this.
The mean?
Yeah, you're right. Yeah, but there's more to it than just the mean. These don't have terms, but this is called normal distribution.
Oh, isn't this like the bell curve?
Yeah, this is called the bell curve. Yes, this shape is the bell curve, and this is actually called, when you're in probability and statistics, this is called the normal distribution. So basically, this part holds 34% of all of the things. This also holds 34%. And yes, this is the mean. Just write it as AVG because mean is basically the average. And this holds 34%. This holds 34% also. And yes, this is the standard deviation. This is the SD. Standard deviation. Negative standard deviation. And yeah, that's basically.
Aren't they like basically symmetrical?
Yeah, it is symmetrical. I can't draw that well. That's why it's like it doesn't look symmetrical. Yeah, but this is supposed to be symmetrical, yes. And this holds 13.5% of all the data. So if you plan on getting into like data science and programming, computer programming, data science, stuff like that, then like this bell curve, normal distribution, probability statistics is like pretty important for you. So this is like 13.5 also. And this small part right here is 2.5%. So I'm just gonna write it out here. 2.5%. Here also. 2.5%. So this holds 2.5% of all data. And yeah, that's pretty cool. So does everybody get this? So yeah, I'm just gonna move on to law of sines and law of cosines. Okay, Rohan, I don't think you know this because like the day before yesterday, it was only me and Sadath, and so we were basically the only ones who learned this. So yeah, law of sines. So this is the law of sines. So everywhere, Rohan, do you know what sine and cosine is? Yeah, it's like, do you remember SOHCAHTOA? I think you know this. Yeah, good job. So basically the law of sines. So instead of only working for like right triangles, where like this angle has to be like 90 or something, this law of sines works for every single triangle on the planet. So yeah, it's pretty important. So the law of sines, basically all it's just saying is that sine of an
Can I say
angle.
it?
Yeah, sure.
Okay, so the sine of angle A over side A equals sine of angle B over side B, which also equals sine of angle C over side C.
Yeah, good job, Sadat. Yeah, this is well said. But what are actually A and B and B and C and C? So let's just label the triangle real quick. And your triangle might not look exactly the same as this, but like the same principle, you know? So let's say you have A, B, and C. So these sides, these are just the angles, by the way, and so these sides are opposite of these angles right here. See, so A, this is A, right? So small a, the side A, is going to be opposite of this, so it's right here. B is right here, and C is right here. And yeah, so sine of A divided by A is equal to sine of B divided by B, which is also equal to sine of C divided by C. So normally you would only use two parts of this at a time, like something like this, or something, or maybe even like this part and like this part at a time. But like we just write it like this, so it's shorter, and like we don't have to memorize like all three of those. But law of cosines is different, which I'm going to show after the meeting ends. So let me just end the meeting, and so everybody rejoin. Okay, so it looks like everybody's back. So let me get back to what I was saying. So we were talking about law of sines, so Rohan, did you get that? Did you get what law of sines is? Yeah. Yeah. You can just say it like sine of A over A and sine of B over B is equal to sine of C over C. You don't have to say side. That's just implied. But it might be harder for you to remember, so I don't know. Just look at what's best for you. So let's now learn about law of cosines. So law of cosines. So basically, this is like just pretty similar to law of sines, but like not really. So this is like used for like the same thing, but it's pretty different. It looks a little bit like the Pythagorean theorem, but it doesn't. So yeah, let's look at it. So it's a squared is equal to b squared plus c squared minus 2bc times sine.
Sine of A.
Yeah. So it's sine of a because you're looking at side A over here. Because this whole thing is equal to side A. If it was side B, then you would have side B is equal to a squared, sorry, b squared is equal to a squared plus c squared minus 2
minus 2AC
Times sine B.
yeah, times sine B. And then for C, sorry,
this is the most complicated.
I wouldn't say that. It's not really. I mean, but this is pretty much the most common, kind of.
Okay.
So you have so you have c squared equals b squared plus c squared. Sorry, it's a squared plus b squared. Yeah, I just noticed. A squared plus b squared minus 2ab times sine of c. And yeah, these three are the individual equations. Yeah, but they're pretty similar, so it's really not that hard to remember. So these are used on the pretty same principle as law of sines. So let me just write them on the same page, and let's look at the commonalities and the differences.
Should we tell Rohan when to use them?
Yeah, that's what I'm just about to do. That's why I'm writing them on the same page. So we have sine of A divided by A is equal to the sine of B over B, and it's equal to sine of C over C. So this is the law of sines law. And yeah, so basically when you use them, it depends on what the problem is. So basically you use law of sines when you have like a triangle. So let's say they give you A and B, and they give you this angle right here. Then you use this. So they give you this, this, and this. That means that you can use this. But if they give you if they give you this triangle, something that looks like this. I mean, these side names don't have to be the same, but yeah, the principle is the same. If they give you something like this, where like the angle is not here, so it should not be here. So this is bad. If you had something like this, then you would use the law of cosines instead of the law of sines. So yeah, it's not necessarily bad, but like you wouldn't use this. So if they give you two angles, and then whichever side, it doesn't matter. So they give you this one, then you would use this also. But if they give you something like this, which we just discussed, so if they give you A, B, and C right here, because like c is going to be right here, and c is opposite of that. So I have to give you something like this, then you would use this to find like the value of c or whatever. And yeah. Or you would also use this when they give you all three sides. So if they gave you A, B, and C, then you would also use this to find like the angles of A and B and C. If they give you all the sides, then you would use this also. So yeah, Rohan, do you kind of understand that?
Yeah, I get it.
Okay. Let's look at what we're going to look at next. Yeah, so that was pretty much it. And the day before yesterday, we learned about the triangle area formula. And no, it's not that old one where it was like triangle area formula. TA. Triangle area stands for some triangle area. And Rohan, you know that old triangle area formula, right? So you have A is equal to 1/2.
Base height.
Yeah, 1/2 times B times H. Yes, everybody knows that, even a third grader. So we don't really need this, right? So, what if you didn't know the height? So normally you would just assume that you would get the height and you could get on with your day, right? But what if you don't know the height? Well, then you could use this formula. So you have 1/2.
Can we also use Theorem's formula?
Yeah, you could use Heron's formula, but like that's super complicated, and I don't like it. I mean, it's just personal preference, I guess. Yeah, I don't use Heron's formula because it's super hard to remember, and I don't know it right now. So I can't tell you what it is right now, so Darth, you would have to search it up. But let's look at this, yeah. So you have 1/2 B times A times sine of C. So this is the same thing as this. And yes, I drew these in very deliberate places. So A times sine of C is equal to H. So H is equal to A times sine of C. So that means that if they give you like a triangle like that, like the one you would use to solve a cosine, the one you would use to solve with the law of cosines. So if they give you like A and B, and they give you C, then you can use this formula to find the area of this. And you could use the area formula, and you could use Heron's formula if you had all three sides. Yeah. But yeah, this is way easier than that because way easier to remember. So yeah, that's basically how you do it. And yeah, that's basically pretty much everything we learned so far. So yeah. We also learned about this thing, I don't remember, actually, so, here's what I'm trying to say. So what I'm trying to say is, we learned about something called the Pythagorean identity. So you all remember the Pythagorean formula, right? I mean, I don't remember what it's called. The Pythagorean theorem.
Yeah.
A squared. A squared plus B squared is equal to C squared, right? So yeah, so this Pythagorean identity is basically the equivalent of this, kind of. It's a bad way to word it, but like, it's the equivalent of this, but for like trigonometry and stuff. So you have Pythagorean identity, so this is basically sine squared of theta is, plus cosine squared of theta is equal to 1. So yeah, that's what it would be. Now I know what you're asking. How can a function be squared? how can a sine be squared? So this is the same thing as, this is kind of the same thing as writing sine of theta squared. So the angle is being squared, and then you're putting it to the sine. So yeah, that's basically how it works. And I don't know how you would use it, but I've never came across a problem where I've had to use it, so I can't really tell you when to use it, because I don't know when to use it. But yeah, that's a cool formula, I guess. That's important in trigonometry. And yeah. I'm pretty sure there's just going to be like problems randomly saying like, find the Pythagorean identity or like something like that, you know? I mean, I think you could use this for like, finding the angle or something, you know? So let's do some practice on this stuff that we learned. Log in. It's loading a lot, so.
Retry it.
Okay.
Area. So basically when you do the end, so area is equal to 1, so h over 2. So b plus b over 2 times h. So h is equal to 2 times 2a times b plus c.
Times b plus c. I don't think it's times b plus c.
I think it's two. I think it's 2a divided by b minus c.
Oh yeah, whoops, divided by whoops.
No, I don't think it's divided by either, because you're multiplying it across, so now you just have, actually, no, yeah, you're right. It's divided by.
No, it's b minus c.
No, it wouldn't, because, yeah.
Oh yeah, because
Yeah.
goes to other side goes divided. Yeah.
Okay, good job, everybody. Go on to the next question. So the rectangle below has an area of 12y squared plus 21y to the power of 5. The width of the rectangle is equal to the greatest common monomial factor of that and that.
What's
So
the monomial factor?
basically it's just a factor. So a monomial is basically an expression with one term. That's basically what it is.
Okay.
Isn't the width 12? Isn't the width 3y squared?
Yeah, good job.
And then the length is 4, so it will be 7y cubed plus 4. Right? 7y cubed plus 4.
Yeah, I think that's right. Let's check it. Yeah, good job. Which of the following is the graph of y equals x plus 4 squared plus 2?
Alright, the vertex is at negative 4, 2, right?
Yeah.
So, isn't it just b? Can you scroll down? Yeah, I think it's just b.
Yeah, it is just b. Good job. Okay, Siddharth, you can do this one.
Okay, we have the expression in the form of y to the power of n. Okay. So the first one is y squared over y to the power of 4 over 5 over 3. Okay, so first you're gonna have to subtract. So we subtract 2 minus 4 over 5. Let me just do that real quick.
6
So that'd be y 6 over 5. So that'd be y to the power of 6 over 5.
Yeah, good job.
Wait,
And
isn't it 2 to the 5 because you're taking the cube root?
yeah, and then I have to take the cube root of it.
And so you would get
And y 6 over 5 and cube rooted.
that would be 6 divided by 15. Because cube root is basically a fractional exponent of
You can
1 over
simplify.
3.
You can simplify. So it's
Yeah.
2/5.
Yeah, it's 2/5. So that's 2. Yeah. So Antonio solving the following equation for y. His first few steps.
I don't think it's necessary. I don't think it's necessary because square root can never be negative. Wait, no, it can be negative, so I think it's yes.
Yes. It is yes, I'm pretty sure. So select all polynomials that have x plus 2 as a factor. Okay, so first of all, I know that it's not this one, because this does not have a factor of x plus 2. See, if you factor x from this, it becomes x squared minus 3x minus 10. And actually, no, it is. No, yeah, it is. Okay, so because after you do that, then
I don't think it is.
it is, actually, because you have negative 5 and then you have 2. And so negative 5 plus 2 is negative 3. So yeah, it is. Tell me if I'm wrong. Okay, I don't think so. Okay.
So The second one definitely does not.
Okay, yeah.
Yeah, you're right. The first one does. The third one does. And the last one doesn't. So I'm pretty sure it does too. You're muted, by the way.
Oh, sorry. Yeah. Okay, so every chemical element goes through natural exponential decay, which means that over time its atoms fall apart. The speed of each element's decay is described by its half-life, which is the amount of time it takes for the number of radioactive atoms of this element to be reduced by half. The half-life of the isotope dubnium-263 is 29 seconds. A sample of dubnium-263 was first measured to have 1024 atoms. After 2 seconds, there were only 32 atoms of this isotope remaining.
I'm confused about this question. I just don't get it.
Okay, so Siddharth, do you know how to do this?
No.
Okay, so basically, let's solve this together, okay? So basically, you have the half-life of isotope dubnium is 29 seconds. So the half-life is 29 seconds. We know that. And the sample of dubnium was first measured to have 1024 atoms. So basically what I would do is, I think I would just have like a geometric series, since it's like exponential decay, instead of, like linear decay or something like that. It's exponential, so I would like make a geometric sequence or a series or whatever. So let me try to make one. So you would have, so the first thing would probably be 1024, and that would be to the power of so we're trying to find t right here, and at first there were 1024. Wait, what am I doing? I don't understand what I'm doing. Okay, so basically, so t is the number of seconds that it was like that. So this is t, and so a n is equal to 32. Actually, no. T would be 1. I don't know what I'm doing. Okay, so 1, and then t, and you have it to the power of k, because k is equal to 1, since 1 is on the bottom right now. So 1, and then, so that would be increasing, and you want it to be decreasing, so you'd have it as 1 over k, or something like that. I think you would have it as 1 over k. Actually, no, you wouldn't. No, you wouldn't. Yeah. Where is that? I'm trying to find. Okay, yeah, it's right here. You would have it as negative k. Because if you have like 1 and 1 is right there, so you would have negative 1, and that would be, no, that wouldn't work either. Okay, so it says the half-life is 29 seconds, and so that means 29 seconds. Let's just take a hint. Let's just take a hint. I'm willing to give up. Okay, so let me just write a random answer in here. So let's get a hint. Okay.
It has to be in terms of t.
Yeah. Oh, okay, so that means, yeah, you're right. It does have to be in terms of t, and t is time. So that, no, it doesn't have to be in terms of t. Actually, no, it does. So t is equal to it's in the form of like an exponential equation, where basically you have like a start value, and then you have like the thing it like decreases or increases by. So that's what you have here, and then you have it to the power of x, I guess. And that's how you do it, I guess. I actually don't think it has to be in terms of t. I think t is supposed to be above there. So that's 1, 2, 4. Actually, no. I don't know. Okay, yeah. So y is actually supposed to be 32 because okay, oops. Y is 32 because it says that there's 32 atoms. So you have 1024 times 1 divided by 2 to the power of x. And we just solve for x now. So first thing we do, we take 1024 to the other side, and that gives us 32 divided by 1024. So that would be 32 divided by 1024, and that's 0.031321.
132, yeah, it's 132.
Yeah. Okay. And then you would have to multiply it by 2, because actually no, you wouldn't have to multiply it by 2. So instead we know, and then we'd have to use logarithms because we would, and Actually, no, we would. So that's 32, right? So that would be 1 over 32. And so it's saying 1 over 2 to the power of something is 1 over 32. And we know that that something is 5 because 2 to the power of 5 is 32. So let's try that out. 2 times, okay, oops. 2 times 2 times 2 times 2 times 2. Yeah, it's 5, and that's 5 twos, and that's 32. So that would obviously be 5 seconds, I guess. Okay, oops. 5 seconds. Check that again. Okay, it's still not right, so let's get another hint.
Wait, it's not asking you for the answer, it's asking you for an equation.
Yeah.
Oh, okay. Well, then we got the answer then. So that's 32 is equal to 1024 times 1 over 2 to the power of x.
And also has to be in terms of t.
It does? Okay, so then that's t.
Yeah, that's what it says.
And you would have to like move everything over there. So just check this. No, that's not right either. I was hoping for an easy way out. Well, I guess we don't have one. So we have 32 divided by 1024. And then you'd have, so we're trying to do it in terms of t. So I'm pretty sure we would have to use logarithms to do that. So that would be,
It's just 5. But you can just write 2 raised to t is equal to 32.
2 raised to 2 raised to t is equal to 32. I don't think that would work. But let's try it. Yeah, it's not gonna work. We have to put it in terms of t, so t is equal to log base base b. So b has to be 1 over 2 because that's what we had that time. So we have 1 divided by 2. And over here, you have 20, no, sorry, 1 over 32. No, actually you have, no, you have 32 divided by 1024. And that's the answer, I'm pretty sure. Nope. Yeah, let's just get the answer. Whatever. Oops. Okay, dang. It's gonna save the progress anyway, so it doesn't matter. Yeah. Okay. Seems like it got us to the next question.
98 over root 2, which we can just write as root 98 over 98 over 2 is 49.
Okay, good job.
Square root.
Okay, so it wants this, so the graph of the sinusoidal function intersects the midline at 0, 5, and then has a maximum point at pi, comma 6. Okay. So the midline is obviously y is equal to 0 or something. No, it's not, because yeah, y is obviously equal to 5 over here. So that means that they're doing something in terms of x or something, maybe. And they want us to find like the formula of the function. So how would you do this?
Midline is 0, 5, then that means diameter
I don't understand your question.
I don't understand like how you find it because I don't know what a sine is.
Okay, so a sinusoidal function is basically the function of sine. So that's like a wave, right? You know what a sine wave looks like, right? Oh, it looks something like this. And it says that the maximum point, and I think it would be flipped or right like this instead. I think it would be flipped like this. Because I think it would. Maybe. Oh, the midline. Okay, I'm wrong about the midline. So the midline is actually, they're saying that the midline as the y-axis. So this is the midline. So yeah, it is actually like this. So it intersects the midline at 5 something and has a maximum point at pi 6. So yeah, I don't know this either. So guys, I think we're going over time a little bit, but basically this is the last class, and so if you like this class or something, then you can join our next class, which is going to be an SIT class, I guess, and it's going to be during the next break. During the next
SIT.
SAT.
Wait, when is it? Like, what date does it start? What time?
Oh.
I think it's during the summer, but I'm not sure. Let me check. 1 second, I'm gonna be right back. Okay, so it's still in the planning stages, but it's during the coming holidays. So it might be during the summer, it might be during earlier time, I don't know. So yeah, that's the SAT thing. Someone, what did you say? I couldn't hear you. Math.
Okay, thanks.
Yeah, I guess that's the end of class then. Bye.
Bye.
See you later then. Okay, yeah.